Hi, I'm Frederick, the micro hobbyist, and in this episode, wait, don't scroll away. I promise you won't see my ugly mug too much this time. Just give me a few seconds, I swear. And as always, yes, there will be bloopers at the end. Everybody loves bloopers, right? Wait, how can I promise bloopers? I just started. Oh, right. I was just imagining future me screwing up this exact script. You know, the one I'm reading right now off a prompter. See that word I just said? Scripted. All of it. Because heaven forbid I have an original thought. What? We're live and I'm rambling like an idiot? Don't blame me. Blame the writers. Okay. I'm being told to wrap up the cold open, so cue intro and roll VT. Did I say you'd see less of my ugly mug? Yeah, I lied. Oh, just kidding. I'm not ugly, just retro compatible. So, here's what's on the menu today. We start with an appetizer of roasted leftovers. Last time's build reheated and served with extra sarcasm. Then an entrée of schematic bolognese, equal parts lines, labels and confusion. For the main course, the chef spécial, spaghetti wiring paired with a fine side of breadboard. And for dessert, you'll be treated to a rich and flavorful code à la mode. So, hungry for more? Want to see some build? In the last episode, we built a NOP tester. The CPU chomped on a hardwired no-operation opcode and dutifully counted addresses like a digital toddler going 1, 2, 3 until infinity. Reset came from the DS1813, which is basically the strict school teacher of reset ICs. Voltage unstable? Well, you stay in timeout for 150 milliseconds and don't argue. Now on to this week's schematic. At the center, the Hitachi HD63C09, rated for 3 MHz, but the datasheets are a tad on the conservative side. I personally ran it at 4 MHz on the breadboard, and there's some brave souls out there who claim 5 MHz. That's like overclocking a rotary phone to play Doom. Ridiculous and insane. Oh yeah, I'm gonna try it. The control pins, NMI, IRQ, FRQ, bus request, halt, and mReady, are all pulled up. Leave them floating, and the CPU wanders off into La La Land like teenagers without supervision. With pull-ups, at least, they stay in line until we wire them properly. For reset, I upgraded to the MIC1232 supervisory IC. Think of it as the DS1813 smarter cousin. It can stretch reset to 150, 600, or 1200 milliseconds. I'm going with 1200, just to be overly and unnecessarily cautious. It also has lower power draw, selectable voltage threshold, and a watchdog input. If the watchdog doesn't get tickled, wham, reset. Perfect for catching when the e-clock isn't running, meaning that our software selectable clock failed. It's just not reset, it's reset with an attitude. Next, bus buffers, the bodyguard's logic. This isn't a tiny build, so signals need muscles to fan out. 2 74HCT 541 octobuffers for the address bus, 1 74HCT 245 bidirectional transceiver for the data bus, 1 74HCT 244 for control lines, half always on, half gated by the bus available signal. Granted, the second half is not that busy. I'm sticking with HCT logic for now. At 5 MHz, that's 200 nanoseconds per cycle. HCT averages 10 nanoseconds in propagation delay, which is most likely just fine. For perspective, even 3 HCT gates in series still leave approximately 170 nanoseconds margin before the next clock edge. A HCT could shave that to 5 nanoseconds, but it does come with sharper edges and therefore more ringing. Like swapping your sedan for a monster truck. Sure, it's faster, but it tears the driveway and frightens the neighbors. If I really need more drive, I can swap later. Now, about that ringing. Every square wave is basically a diva. It refuses to sing one clean note, so I sprinkled series damping resistors on key lines. They don't kill ringing, but they take it from a feedbacking garage band to a half-decent studio demo. Think of them as volume knobs. Turn the squeal down without killing the music. I may change resistor values later to tune it, because every board is its own finicky instrument. Capacitors? It's the snack bar for silicon. Bypass caps, typically 0.1 microfarad ceramics, are very close to each IC's VCC. They're like Red Bull shots, handing out energy at nanosecond speeds. Bulk cap, on the other hand, ranging from 10 to 100 microfarads, sit along the rails like big water coolers, handing out gulps when the whole crowd gets thirsty. Together, they keep the power rails from looking like a cardiogram in a horror movie. The build itself. I lashed together 3 breadboards, this time with extra side rails. Why? Because last time I had voltage drops all over the place, like a power grid in a thunderstorm. With side rails, electrons get more highways. Fewer traffic jams, fewer brownouts. Power enters from the right, flows into the center rails, and then back out to the left, evening out any voltage differentials, if any. Later I might sprinkle in tiny mini voltmeters, like radar guns to catch electrons speeding, or worse, slacking off. Alright, time to go full spaghetti artist. I'll try to place all the components evenly across the breadboard, because chaos is fun, but chaos with symmetry is even better. I debated skipping damping resistors, but let's do this properly. They're like flossing. Nobody wants to, but future you will thank you. Next up, pull-ups on NMI, IRQ, and FRQ. Then halt, mReady, and bus request. Because if you don't leash these pins, they wander off like toddlers in a candy store. Power goes to all the ICs. Connect the reset switch to the MIC1232, and its reset output to the CPU's reset input. Then the CPU's E-clock feeds back into the watchdog strobe input. So, if E-clock dies, the watchdog freaks out and resets everything. BA lines get connected, a few grounds tied down for output enables here and there. Then the read-write line heads into the 244 and 245 buffers. Wire in E and Q lines for good measure, and no, those aren't optional. Skipping them would be like leaving the brakes off your car. Data lines next. The keen-eyed viewers will notice that I reversed the bit order between CPU and buffers. But don't panic, after the damping resistors, everything straightens out, like a bad haircut growing back. I'll reshuffle BA lines on the address bus buffers to give the resistors more elbow room. Then it's address lines after that, so A0 to A7, then A8 to A15. Quick sanity check, and let's not dwell on this too long, so I'll just do a quickie hardware knob again. Hook up the bar graph LEDs, the same 555 timer for the clock, wire the address bus, and wait, what's that? Definitely not supposed to do that. Time for troubleshooting. It was supposed to be simple and quick, they said. Wait, reset line looks suspicious. Low when the button is pressed, but floating when it should be high? The switch? Nah, didn't think so. MIC1232? Not at all. CPU? Definitely not guilty. Well, what does the datasheet for the reset IC say? Blah 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 blah. Oh, there it is. Open drain output. How did I miss that? Probably blinded by the typical application circuit diagram in the datasheet. See? No pull-up. Coupled with the fact that the DS1813 didn't really require one too. Classic trap. Solution? Well, add a pull-up resistor. Boom. Fixed. So long, hardware knob tester. Time to be replaced by your virtual counterpart. I pre-prepared some DuPont cables. Is that even a word? Pre-prepared? Sounds like Department of Redundancy Department. Anyway, I plug in the low address bus, the high address bus, the data bus, then the clock output, and E, Q, and read-write as inputs. Oh yeah, I forgot to run the read-write line from the buffer to its damping resistor. Now it's time to dust off the memory cells and write some Arduino code. Let's see if Silicone Spaghetti can dance to our retro synthwave tune. Before we dive in, let me share why I keep going back to PCBWay. You know, I get asked a lot, why PCBWay? Well, here's an honest answer. The quality of their PCBs is consistently excellent. Solder pads where they belong, crisp traces, everything lined up exactly as KiCad said it should. When you spend weeks designing something, it's a relief when the board that shows up just works. And it's not just PCBs, I've had sheet metal parts made through PCBWay too, and the quality is just as impressive. Honestly, it's like they shrink wrap your CAD files with your dreams into reality. Of course, they also do 3D printing, CNC machining, injection molding. Basically, if you can dream it up, they've got a way to manufacture it. But what I really appreciate is this. They deliver the same care and precision across all of it. That's why I keep going back to PCBWay. PCBWay isn't just a service, they're the quiet partner that makes my hobby look professional. And hey, did you know PCB actually stands for Purple Coated Beauty? You know it's true. Let's virtualize the world-famous knob test. We start simple, a basic clock output. Digital write high, wait 25 milliseconds. Digital write low, wait another 25 milliseconds. Congratulations, you've just invented the Arduino sundial. But before that, we declare the clock pin, set it as an output and setup, and default it to low. Starting high would be like starting a microwave with the door open. Oh, and document as you go. Otherwise, future you will stare at this code like it's the Rosetta Stone. Also, it's a fine time to spin up the serial port as we'll need it in the future. Now interrupts. Relax. It's easier than it sounds, but I won't lie, I didn't think so at first. All you need to do is declare the CPU's E pin, set it as an input, then attach an interrupt to it. And bam, the Arduino now reacts instantly whenever E changes. Just like your golden retriever when you rustle a bag of logic chips. But we need a handler function. Let's keep it simple. If E is high, turn on the onboard LED. If it's low, turn it off. Don't forget to declare the LED pin. Compile. Syntax check. Oops, variable name mismatch. Good. Fixed. Recompile, upload, and no blinking. It was supposed to be simple, they said. Any 2-year-old could do it, they said. First unsubstantiated guess, is the clock too fast? Slow it down, and no. Second stupidest guess, pin 13 instead of LED built-in label. Not that either. I don't even know why I bothered. Third guess, sprinkle in some serial print statements, in an ISR no less. Now, that's a programmer's duct tape solution, if ever there's one. And bingo. Yeah, but no. The code clearly runs in ISR, but the LED never turns on. Oh, that's because I forgot to pin mode it as output. Rookie mistake. Compile and upload, and now the LED finally blinks like a disco ball. Now that it blinks, let's add some flair. Toss in some silly serial print text and setup to prove we're alive. Then, onto the important part, properly reading the address bus. Bit by bit, A0 through A15, captured using bitwise operations, return a 16-bit value. Like sewing 16 socks into one giant nerd scarf. Don't forget to declare all those address pins, because looking like a fool twice in the same 5 minutes is only reserved for yours truly. And while we're at it, declare the data pins too. Because the address value will be shared between the interrupts and the main loop, it's declared as a global and volatile variable. Translation: Dear compiler, hands off. The interrupt will mess with this whenever it wants. I shall name it G-address, because when it comes to naming things, just call me Mr. Original. For print control, we create a Boolean flag gprint pending. Whenever we capture an address, we set that flag to true. Back in the loop, we know for a fact that our caveman clock won't cut it. We need logic to do stuff during the high phase of the clock cycle. So we use millis to save the last tick in a variable. Then do a loop while the difference is under 25 milliseconds. Instead of a numbered value, define a constant named half cycle so we can adjust it later without digging through spaghetti. Remember that gprint pending flag? If it's true, temporarily disable interrupts, because nothing says stable data like telling the CPU to shut up for a second. Ooh, no, I'm not trying to make a parallel with this metaphor. I wouldn't dare, I do value my miserable life. Then set the print pending flag to false. Copy the address into a local variable to minimize data corruption, should the interrupt be triggered in the meantime, but we all know it won't. It's just good practice though. Then re-enable interrupts, because you don't want to stay deaf forever. We print a 16-bit address on screen, extracted with bitwise operations, all lined up in binary. Imagine this headline: Arduino now auditioning for binary idol. What, too corny? Of course, a NOP test needs a NOP opcode. That's hex 12, in case you forgot after me saying it for about 1500 times. We make a write databus function, push the bits out with bitwise voodoo magic, and appropriately drive each databus pin high or low. Let's rename the loop counter from bit to index, because nothing confuses people more than a variable named after an electrical concept. Now let's set the address bus as inputs and the data bus as outputs. Yes, I'm lazy. Cut and paste. Deal with it. Then call write databus with the hex 12 value to actually spit out the opcode upon reset. We always need a sanity check time. Compile. Of course, error. Why am I not surprised? Missing semicolon, because that never happens, ever. Seems to be a programmer's rite of passage. Compile again. Another error. With all these errors, I'm starting to feel incompetent. And, well, that would be justified, especially with a simple missing equal sign. This is why we drink coffee. At this point, my editor should just cut these typos out, but no, let's make me look like a moron instead. Compile again, upload, and success! Well, it runs, but the outputs are all zeros. Classic. You know the adage? To err is human, to really screw things up requires a computer. Well, for a computer to screw things up requires an error-prone human, and in this case, I'm that foolish human. Did I set something wrong? Maybe these values needs to be true. Nope, still nothing. Wait, operator error. Yeah, literally and figuratively. Let's fix this, and no, I'm not even going to go there and mention the pipe symbol and the words mouth shut in the same sentence. That's enough self-deprecating humor in one day, don't you think? Compile, and suddenly magic. And as Adrian Black would say, it freaking works. Didn't I say you'd see less of my charming mug? Well, not in those specific words, but yep, I said it and I stand by it. Yeah, I'm charming. And Nick? Yeah, you're jealous. As promised, this episode was more benchcam heavy and more code on screen. And you can't say I lied about that. But you did manage to watch this to the end, so you're all saints for tolerating me. Thank you all. So tell me, did you enjoy it? Did you learn something? And did you chuckle at my questionable humor? Or did you just think, wow, this guy's a bumbling idiot? If you answered yes to any of those, mission accomplished. Did I really need to say that part aloud? On camera? Ugh. Okay. Anyway, please do all of the YouTube rituals. Like, subscribe, and yes, tickle that notification bell because, like Dave Plummer says, I'm only in it for the likes and subs, and clearly, I'll never make a dime off YouTube. I wish. Before we go, let's bow our heads to the retro gods with this prayer. Zilog, Motorola, Moss, Hitachi, Commodore, even you, Sinclair, despite your wobbly keyboards. May your clock stay stable, your capacitors stay fresh, and may no chip ever be inserted backwards. Blessed be the vintage silicon. Thanks for sticking around, and see you in the next episode where programmable logic devices go head-to-head with the 6309. Place your bets, folks. Silicon Showdown incoming. Yes, there will be bloopers at the end. Bloopers. Bloopers. Wait, don't go... Just hit record right now. Record. Again. Wait, how can I promise bloopers? I literally just hit record just now. I literally just hit record. I just started to record this. How can I promise bloopers? I just hit start. I was just imagining future me screwing up this drink. And as always, yes, there will be bloopers. There will be. Really? The quality of their PCBs is consistently. One take, please. Impossible. Me, one take? 100 take Fred. That's what I'm called. We get asked a lot. We? No, I get. Here's the non-est. It's a non-est answer. Traces. Chip. Crisp traces. They're quite they're and you're all saints for tolerating me. I'm not, I'm only in it for life. Shoot. Please do all of the YouTube rituals. But datasheets are a tad on the conservative side. Conservative side. Or the dynamo with side rails. Fewer traffic jams, fewer brain. Cluck output. Cluck. To dust off the brain cobweb. Can dance to our retro synth wave, just like your goal, extracted with bitwise. Now let's set the address bus. Then call. I'm tired. First choose another word.